Good morning, guys. Anjani Kumar here, dealing instrumentation subject for a final year electrical students. In the last session, we discussed about ramp type digital voltmeters, right? Till now, we have completed about three types of digital voltmeters: the counter type digital voltmeter, successive approximation type digital voltmeter, and ramp type digital voltmeter. In our last session we did this thing, right? Today we are going to discuss about dual slope integrated type digital voltmeter, right? So before start the session, I just want to give a brief review on ramp type digital voltmeters, right? So you know the block diagram and all these things. I don't want to explain the block diagram analysis again. So in a ramp type digital voltmeters, why we are calling ramp type digital voltmeter means we are having a ramp generator. So with the help of ramp generator, we are converting whatever the analog data into digital form. So that's why we are calling ramp type digital voltmeter, which is having two comparators, one oscillator, one gate and counter. After that, the display system will be there. Right, so whatever the input signal that can be applied to the ranging or attenuator. So what is the purpose of ranging and attenuator? The ranging which increase if your input value is very less, the ranging means it can increases the value. Attenuator means it can attenuate the quantity that you are going to measure. Right, so after that will enter into the input comparator. So input comparator requires a two input. One input is the unknown input and the another one is the ramp input. So whenever the input greater than the ramp input, it will generate the start pulse to the gate. The gate will open and oscillator will send the clock pulses to the counter. The counter will start counting. So when number of clock pulses enter the count, that will display on the screen. Up to when the gate will open means there will be another ground comparator. So in this, it is having two inputs, that is called a ramp input and a ground. Whenever the ground which is greater than the ramp input, definitely it will send a signal to the gate, stop the gate. So then the gate will stop and it stops whatever the clock pulses it entered to the counter. So then the counter will decide, okay, we need to close the clock pulses. So counting the clock pulses, and it will display the binary data. And we have a sample, and at that moment the counter will send a signal to the sample and hold circuit. It will set that okay, you have to generate another ramp signal for another analog to digital conversion process. Like that, you know that ramp type digital voltmeter, it's not that much efficient to explain with a block diagram itself. That's why I just review on that. Okay, now the very important concept that tomorrow's sessions are very important sessions. So definitely among all the DBMs, the best DBM, so that is called dual slope or integrated type digital voltmeters, right? Right, so this is very important. Right, it's a somewhat difficulty will be there. So if you follow my videos, definitely you should overcome the difficulty also. Right, so I hope definitely I'll clearly explain the whole concept of dual slope or integrated type digital voltmeter. Right, so so you know that dual slope integrated, so that name itself indicates there are two slopes. So we have a digital voltmeters like a single slope digital voltmeter. Right, so there are two types here: single slope, right, dual slope. So each and every digital voltmeter that it has some advantages, right? But the single slope which is having a more disadvantages, right? So that can be overcome with the help of a dual slope integrated type digital voltmeter, right? So here I just want to explain, definitely my session, I will explain how the session will be and all these things. In a single slope, whatever the output voltage, which must be depends on R and C components like resistance and capacitance, right? So in a single, if you do the experiment with the help of single slope DVM, it's very, whatever the voltage that depends upon R and C, right? So definitely if the time goes on, there will be an aging of R and C, there will be some drift, right? So R may be reduces, C may be reduces, right, due to the aging, right? So definitely whatever the output must be depends on RC means, so definitely you will get the output should be vary, right? For suppose if you do the experiment, you got the result as V0 is equal to 100. After 1 year, you see after 1 year, definitely the output must be depends on resistance and capacitance now. So there will be an aging effect on resistance and capacitance. So definitely it will show the wrong values. It will show the somewhat wrong values. So, with that you will get the result as somewhat 101. So there may be a change in voltages, change in output. So that's why this can be overcome with the help of dual slope. In the case of dual slope, you don't have any output, doesn't depends on R and C. Output doesn't depends on R and C. That means we don't have any changes in output whenever you do the experiment. 2 years later or 3 years later, whatever it may be. So definitely you'll get the accurate result. Right? Among all the instruments, I hope it's clear what is a simple difference why we are calling a single slope and dual slope. In a single slope, whatever the output voltage must be depends on R and C components. Alright, so with the help of R and C depends means definitely due to the aging after 4 years after, definitely you will get a different result because due to the aging your resistance capacitance may show the wrong values, right? But in the case of dual slope, we don't have that much variations. Your output doesn't depends on a resistance and capacitance. So that's why we implemented our concept called dual slope integrated type. Right? In all digital voltmeters, so these DVMs, these dual slope DVMs are a more accurate instrument, very important. So these are more accurate instrument, right? So whatever among all the digital voltmeter, which one is a more accurate means the dual slope integrated type is a more accurate instrument, but it has a time consuming, right? So but it has a time consuming. So whenever we require, if you want to require a more accurate result, with definitely there will be no problem for you for our time consuming, then you will go for this dual type of digital voltmeter. So time is not that much important. If you want a really accurate result, then we'll go for dual slope integrated type, dual slope or integrated type digital voltmeters, right? We will use digital multimeters is there now. So these type of multimeters that require accurate results between the 2 points, either voltage or current, whatever it may be. At the time doesn't part, right? So we don't consider a time on this, right? So whatever the DMM digital multimeter which working on the basis of a digital dual slope integrated type digital voltmeter, right? Why? Because that digital multimeter that requires accurate results between 2 points, either voltage, current, resistance, whatever it may be. Alright, this is a somewhat introduction about dual slope integrated type. Alright, so I just want to divide my session in 2 parts. Right, the first part first part, I'll explain what is the concept of a single slope DVM. So definitely, if I go with the help of dual slope integrated type, so you won't understand, because if you understand a single slope DVM, so definitely it will be good for us to easily understand the concept of dual slope. Alright, that's why first I consider a single slope DVM, how it will work. How it will work. After that, we'll discuss about dual slope digital voltmeter. Alright, I hope it's clear. Right. Now, before going to single slope DVM, I'll start a single slope DVM. Right. So before going to single slope DVM, these type of these type of digital voltmeters are indirect voltmeters, right? So these are indirect methods. Indirect meters. That means you won't get directly a analog to digital conversion, right? So you won't get analog to digital conversion, right? So first, whatever the analog data which is converted to proportional time, right? So first analog, it is not the direct conversion. So it converts, like, first whatever the analog data, that is nothing but unknown signal, unknown input, which we want to convert into digital form. So whatever the unknown analog signal which is converted to proportional time, right? So after that, whatever the time which is converted to digital form, right? So we require a mechanism that will convert this time into proportional digital voltage. So whatever the digital form, numerical form, right? See, so it's an indirect method. You won't directly convert your analog data into digital form, right? So basically, first whatever the analog data which is converted to proportional time, right? After that, whatever the proportional time which is converted to digital form. So like that, this type of dual slope or integrated type, either single slope or dual slope integrated type DVMs will work, right? First, the process is, first whatever the data which is converted to analog to proportional time, analog voltage to proportional time, how it will convert. So for this we require an integrator. For this we require integrator. So that's why we can call it as an integrated type DVMs, right? Right. So whatever analog data first which is converted to proportional time, how it will convert? So with the help of integrator, we will convert analog data into its proportional time. Alright. So I'll explain each and every concept, how it will convert and all these things, right? After that, so you require integrator here, right? So after that, whatever the proportional time which is converted to digital form, right? So for this we require a counter. Right? So which will count at particular time period that given from analog data how many clock pulses that are entered. So it will count how many clock pulses that are entered, that will display on the screen. So whatever the digital form that you are getting, right? So whatever the digital form that you are getting depends on how much time, right? What is the time will depends on analog data. Likewise, whatever the analog data which is converted to digital form. I hope it's clear, right? So these type of digital voltmeters are indirect voltmeters. You won't get directly analog to digital form, right? The first, whatever the analog data which is converted to proportional time. So with the help of integrator, alright. So after that, the proportional time which is converted to digital form. That in that time period, how many clock pulses that you are applied. So how many clock pulses that you are applied, that make digital nature, right? So whatever the digital data you are getting, which is proportional to the time which is proportional to the analog data. So whatever the analog data, we are converting into digital form. For a time to digital form, we require a counter. For analog to proportional time, we require an integrator. That's why we are calling integrated type digital voltmeter. I hope it's clear. Right? Now we'll see what is integrator. How it will convert from analog input to proportional time. So that's we need to understand. So this is simple concept, but from basic knowledge, it will be very helpful. Alright, if you know the basics, definitely it will be good for you. First, we'll discuss about. Now we'll start the concept of integrator first. So with that, if you know the integrator, the first part is nothing but your voltage, which is converted to proportional time. So that means how it will done means it with help of integrator itself, right? The first you know the integrator. So after that we'll discuss up the counter. Then we'll start the single slope digital voltmeters, right? The first integrator. Alright. So that means how your voltage, analog input voltage, which is converted to proportional in time. Right, how it will convert, we'll see. Right, you know the block diagram of integrator, how it will works, right? So how the block diagram of integrator. Right, this is the ground. This is OR. And this is C, this is output, right? So you know that the integrator which is having, you are having a two inputs, that is V in and V reference. You will integrate the V in also, or else you will integrate the V reference also. That's your choice, right? So that means both V in and V reference both are opposite phase. You know that for a given input, so if you give a positive voltage, you will get the negative output. If you give a negative voltage, you will get the positive, because it's like a inverting comparator, right? So minus plus is there. That means you will give a positive, you will get the negative. You will get a negative, you will get the positive output voltage. For a simplicity, I am using negative V reference. You will go anyway, right? You will go for positive V in, you will go from negative V in, whatever it may be. I am inverting minus V reference value. That's it for a simple thing, right? Right. So with the help of integrator, how faster my output voltage change? How faster my output voltage change? Faster my output voltage change is directly proportional to the input that you are giving, right? So how faster my output voltage changing depends on the input, right? See how it will be. You know the output of integrator. So you know the output of integrator V0 is equal to minus 1 by RC integral V in dt. Right? So you know the formula of the integrator, right? So whatever the input, that is nothing but my V minus V reference. So that is a constant value. So minus V reference is my input, that you assume, right? You will get V in is nothing but minus V reference now. So that means plus V reference by RC integral dt. Any doubts? Right? So now I am doing dV0. Right? So I am differentiating with respect to t. Right? So you will get dV0 by dt is equal to 1 by RC. Integrator and differentiation both are cancelled out. V reference. Right? So for simplicity, you just assume whatever the V reference is my V input now. You just assume whatever the V reference is my input, right? Here, so dV0 by dt is equal to V in by RC, right? Right? So here you will see 1 by RC is a constant value, alright? So dV0 by dt is directly proportional to V in, right? So what is dV0 by dt? The rate of, for how much rate of change of output voltage. That means how much faster rate, that means time dependent. Rate of change of output voltage is directly proportional to the given input. That means rate of change is nothing but time na, is directly proportional to V na. So whatever my voltage which is directly proportional to the corresponding time. I hope it's clear. Right? I'll explain, right? If you won't understand, we'll see a graphical representation. With that, you will clearly understand. Right? You know everything. Whatever my input voltage must be depends on, but must be converted to proportional time. Right? See, rate of change, you know d pi by dt means rate of change of flux. Particular time, it depends on a time, is directly proportional to, time is directly proportional to the given input, analog input. Right? My analog input voltage which is converted to time. Hope it's clear, right? See, you will see. Right? So this is an integrator. Minus plus. This is a ground. So this is the given B reference that you are giving. This is the output, right? So whatever the input that is given as minus V reference, right? Or suppose, so this is minus V reference is the input that you are giving, right? Which gives the integrator, right? So how you will get the result? So step input integrate means definitely you will get the ramp input. So how the ramp input will be? This is a negative, you will get the slope as a positive. So that means this is a ramp. What is the slope? V reference by RC. That means how you are getting a positive slope means if you are giving a negative, you will get the positive slope. It means you know that V0 is equal to V reference by RC. Right? You will get the positive slope integral to Vt. Right? You will get the positive slope. Now, for suppose I am having a different types of input. With that you will clearly understand my input voltage must be depends on a time. Right? Right? You just assume this is my one input. Another input that I am taking much greater, right? So this is second input. And another input that I am taking somewhat faster, right? Somewhat more. Three inputs, right? I am giving to the integrator, right? How it will be? See, for a given first input, so how the show will be? Either whatever it may be, a positive or negative. If you give a step input, you will get the ramp input. That's it. This is for first one. If input voltage is more faster. This is for second one. If input voltage is even more, it will more faster. So these are the three waves ramp input that you are getting from integrator, right? But suppose you just assume a constant voltage. See, this is my constant voltage. This is my input, that your is analog input, right? Right? See. Right? For a given analog input, for a first waveform, that requires how much time? This much time is required. For a second voltage, that means even more voltage, that require this much voltage. This is T1, T2. For a third waveform, that is even more voltage that you applied, it requires T1 time. So don't you think that definitely whatever the input voltage, that must be depends on a time value? For a given input, the first waveform required T1 time to integrate. Second waveform required T2 time to integrate. Third waveform required T1 time to integrate. So that means whatever the voltage which is directly proportional to T, either increase or decreases, whatever it may be. So what is the voltage? That voltage that you are giving analog voltage. That depends on a time. Na? So whatever the statement is true now. So that is a mathematical statement. Now we are graphical representation. So that means we are converting whatever the analog voltage which is converted to time. Right? Now the first part is over. I hope it's clear. Nothing is there. Simple. Whatever the rate of change is directly proportional, change of output voltage, that is nothing but directly proportional to the input. What is the input? Analog voltage. What is the output? Depends on a time. Alright, so that's the first step that you cleared. Now the second step, the first step is V is directly proportional to T with the help of integrator. Whatever the input is directly proportional to the how much time. Right? Next step, the time is converted to digital form. Right? How it will convert? So for this we require counter. Right? You have a counter. Right? So the counter will count how many clock pulses. Right? How many clock pulses. So that will display the result, digital display. It proportional to the how many clock pulses. Right? Who will send the clock pulses? Right? We have a AND gate. Right? So AND gate will generate the clock pulses. Right? So this AND gate clock pulse depends on, if AND gate should be operate, when AND gate operates, both are high. The clock pulses is high. It depends on whatever the input that you are giving. So that input is nothing but the time. Hope it's clear. So whatever the another input that is given to the integrator. So this time depends on whatever the voltage that you are applied. So that is the analog voltage that you are applied. See, one more time up. I'll explain one more time. So you know voltage is directly proportional to T, whatever the analog voltage that you are converted to time with the help of integrator. One part is over. After that, whatever the time which you are converted to digital form. For that we require a counter. Right? I have a counter which count how many clock pulses. How many clock pulses? Who will send a clock pulses? So which counts how many clock pulses, that will display the digital. So my digital output directly proportional to the how many clock pulses that are getting. So how many clock pulses? Who will send the clock pulses? There will be an AND gate. So one end of AND gate will have a clock pulses. Another end of AND gate will given to the time. Right? So time, that is nothing but output of integrator. Right? So this time which is directly proportional to the voltage, given analog voltage. Right? If these two are high, then only the clock pulses will enter, the counter will count and will do the display. So whatever my digital, whatever my analog, which is converted to digital form. Na? Right? For suppose, for a given voltage, you will get the time like this. Right? My voltage, which is converted to particular time. So this is the time up to this time. My input signal is high. In that period, how many clock pulses? that it allows. That means in that period both are high. How many clock pulses? 1, 2. There are 2 clock pulses. 2 clock pulses enter, the counter will display 2 digit, 2 value. If the time is more, right? So what happens? The number of clock pulses will enter, right? So how many clock pulses? 5 clock pulses will enter, it will display 5, right? If time is less, right? So how many clock pulses? Only 1 clock pulses will enter, it will display. So whatever the time, so who will develop the time? This time is depends on applied analog voltage. I hope it's clear. Alright. So whatever the time which depends on given analog voltage, that means whatever the analog voltage which is converted to time. Alright. So in the time, how many clock pulses that you are given to the counter starts counting, that might result. See, I hope it's clear. If you have any doubts, I'll explain one more time. My first step is over. V is directly proportional to T. So whatever the analog voltage which is converted to time. Alright. Next for this time is converted to digital form, that which we require a counter. We have a counter. Alright. So this counter which is having how many, this counter will count how many clock pulses, that my digital display. Right. So who will send the clock pulses? We have a logic AND gate. Right. One end of AND gate will count the clock pulses. Right. Another end we will give the integrator output. So what is that integrator output? T. Right. So T is directly proportional to whatever the voltage that you have. That is analog voltage. Right. If for a given analog voltage, this much time is there. Right. In this much time, how many clock pulses that are allowed to the counter? If it is high, both are high, AND gate will high. 1 into 1, AND gate will high, it will send a clock pulses to the counter will display. Alright, so whatever the time, this much time depends on how much voltage that you are applying. If time is further greater, that means if time is greater, that means more number of clock pulses that will allow. Alright, so how many clock pulses? 1, 2, 3, 4, 5, 6, 7, 8. 8 clock pulses will allow, 8 will display. Right? If time is less, right, how many clock pulses will allow? Just 3 clock pulses will allow, the 3 will be displayed. So like that, these type of DVMs will work. Right? I hope it's clear how the concept, right? I'm not entering to the block diagram. I just want to explain how the integrated, how the digital voltmeter, right? Integrated digital voltmeter will work. First it will convert voltage to time, and time it will be converted to the digital form with the help of counters. Right? Now we'll see the single slope digital voltmeter. Right, single slope digital voltmeter. Right, we have a integrator, whatever the integrator output which is given to the comparator, inward comparator. So this is my V input, you are integrating V reference. Right? Right? So first you will observe this diagram. Right? Right? The first you will observe up to now. After that we'll go for a logic. Right? Here the comparator is an inward comparator, So which is having a two inputs. One input is nothing but inverter input, another input is nothing but unknown input. Which unknown input, which you are converted into digital form, right? See, right? So this is my unknown input, right? So this is my unknown input, right? Now, so this is the output of an integrator, right? Now we have a reference value, so which is have something reference value. If it is a positive or negative depends on your polarity, your wish, but I just want to explain. It's a positive slope that you are getting, right? Right. So this is a standard reference value. You know the reference, which is a constant value, right? Which is given to the integrator. So what? How you get? You will get the ramp value, right? Now you will start the process. So you will give the input to the one end of the comparator, and the reference is given to the integrator. Now the integrator starts integrating, right? You will get the ramp value, right? You will get the ramp value. You will get the ramp value, right? Right? Now we'll see at this point of time. See, at this point of time, right? So here always, right? From here you will see whatever the input voltage always which is greater than the ramp voltage. That means positive which is greater than the negative always, right? So positive is greater than the negative, then the comparator will allow, right? See, comparator will allow. It will gives. See, we'll see a further diagram. We'll see. If positive is greater than negative, the comparator will set 1. Hope it's clear. Here, this is the input voltage. So this is a ramp that you are getting integrated, right? So if you keep on minus our positive signal which is greater than the negative signal, so that means your integrator, your comparator will show the set symbol. Keep on increasing, keep on increasing. At this point, see, whatever my input which is equal to the integrator output. So then what happened? This is a differential comparator, na? Both are equal, right? So if both are equal, so what is the output? There is no output. At this situation, it will give 0 value, right? Hope it's clear, right? So whatever the analog data which you want to convert, which will give to the one end of the comparator, positive side, negative side which we give to the reference value, that is a standard step signal which will be integrated, that can be applied across the signal. So this is my input voltage which you want to measure, right? And this is the reference value which we give the integrator. So then the comparator will compare. Here my input which is greater than the negative value, no problem, no problem, no problem, no problem. So at this point, this we can call it as a trip point. You will see at this point, whatever my input voltage which is equal to my output voltage, that means ramp. So this is the input, this is the output ramp. So at this point, what happened? These two are equal, means whatever the output of a comparator is at 0, it will set 0. Now from here you have a clock signal, right? Here you will have a counter. Here you will get binary data. This is a AND gate. This is a counter. These are the clock pulses. This is a digital form. Now see the magic, right? Okay. So if V in, that means V in greater than V input, which is greater than the ramp output, right? So up to now, this is a signal 1. So both are high. It will send a clock pulses to the counter. The counter starts counting. So it will display the digital form. Right? So whenever V in, which is greater than, at this point V in is equal to the V output, ramp output. So then what happened? This will go for 0. Right? If 1 is 0, 1 is high, output of AND gate is 0, it will stop the clock pulses. It doesn't allow the clock pulses to the counter. So the counter counting stops and it will show the display. Hope it's clear. So this we can call it as a time period. Like that, how the single slope, only one slope is there now. So that you are getting, so that is called as, that's why we are calling a single slope a digital voltmeter. I hope it's clear how it will work, right? So what is the output voltage of this one? Minus 1 by RC integral V in dt. So whatever the output voltage that you are having, RC component, that means slope is nothing but V in by RC, V reference by RC, whatever it may be. The slope which is having a RC component, output voltage which is having a RC component, right? When further using after more number of years, definitely there will be aging in a resistor and capacitors, right? Due to that aging, so definitely it will reach an error value. I hope it's clear from my side. What is a single slope DVM means? You know about the functioning. V is converted to time. After that time, how many clock pulses that you applied at that time, that will counted by the counter will display. This is the time now. In this time, how many clock pulses that the AND gate will allow? So that much clock pulses will reach. Right? We have a comparator. So one end of the comparator which is given to the input, analog input which you want to measure, right? So another end which is given to the reference, right? So reference value, it should be always a constant value which will given to the integrator. So integrator will develop a ramp signal, right? So this is my unknown input, right? Unknown input. When comparator, when you given an integrator, it will generate a ramp signal. Okay, it start generating a ramp signal, right? So here up to this point, whatever the V in which is greater than V naught, so that means definitely positive which is greater than negative, it will send a signal to the AND gate, right? AND gate output both are high, definitely the clock pulses will allow, then the counter starts counting, right? So when at this point, how many, at this point, you will see this point, whatever the ramp and input, this one and this one, both are equal, right? At this point, if these two are equal, whatever the output of the comparator is 0. So then one end of the AND gate is 0, another end is high, output is 0. It will stop. There is no clock pulses to the counter. The counter counting will stop and it will show the result. So whatever the result that you are getting, which depends on how many clock pulses will depends on how much time that integrating takes place, right? What is how much time? If input voltage is even more, the time is even more. That means whatever the voltage is directly proportional to the time. That means the clock pulses are more, the output is more. Like that you said, right? I hope it's clear from my side. So this is the concept of single slope DVM. If you have any doubts, we just I just explained the basics. What is the concept of integrator? How my voltage is converted to time. Here the first my voltage which is converted to time. So after that time is converted to the pulses. That pulses is going to be counted by the counter, right? With the help of counter, the time is converted to digital form, right? So which is having a only single slope, so that's why we are calling it as single slope digital voltmeters. Thank you for now. In the next session we will discuss about the dual slope integrated type digital voltmeter. Thank you.